Hey guys, Professor Doney back here, and the last problem with dealing with friction with one-dimensional motion. We'll eventually talk about friction when we go around corners in circular motion, but for now we're talking about friction when something is sliding. So this problem here is an object, our box, our 10 kilogram box, is sliding along at this velocity, 20 meters per second. When it encounters, right here, some rough surface. You know, it could be you're sliding on ice and hit gravel, or I don't know, it's just sliding along, all of a sudden it hits some rough piece. It has a coefficient of this and eventually comes to a stop where our final velocity is 0, and we're asking what's the distance to come to a stop. So how do we look at this problem? Well, we're involved with friction, so we're going to have to use the friction equation, I suspect, at some point. We already know mu. We have to find f of n. I'll put a little question mark there. Where do we find f of n? We find it from summing forces vertically in the y direction. How do we do that? We have to draw a free body. So we're going to start off again, which is pretty standard for any problem that has forces involved with it, the free body diagram. So there's our box. It has mass, so it'll be mg down. It is on the ground, so it'll have an f of n. Now, are there any other forces involved in this? Well, there's nothing pulling it to make it go that speed. We're just told that's how fast it's going when we observe it. This is observational science, and that's how fast it's going. But when it hits here, we get some friction, right? So I'll try to get that blue color again. We'll get some friction, and since it's moving this way, I'll put V that way, friction will act this way to try to slow it down. Okay, it acts in the opposite direction, because friction is actually the force that causes it to slow down. Friction is the force that causes it to decelerate. Okay? So friction will end up going into our F equals ma equation. So if we go through this, and we're going to sum forces in the y direction, we set it equal to 0, because we know it's going to leave the table. We can go through like we've done before, mg, Fn equals mg, it equals 98 newtons, because it's 10 kilogram box, and we've done that before. Now once we have that, we can kick it back in here and find out that our friction is 0.5 times 98 newtons, which is 49 newtons. That's how much friction is present between that box and that rough surface there in blue. Okay, so that is that 49 that's causing it to decelerate. So we're going to go next to some forces in the x direction. Now since we know it's already moving, I don't set it equal to 0, I set it equal to ma, and I'll put a little x there to remind us it's horizontal. Call plus to the right. We sum forces. The only force happening is friction. Friction is actually in the opposite direction. It opposes motion, so that's a minus 49. Our mass is 10, there's ax. And we come up with ax equal to minus 4.9 meters per second squared. That is how much it's going to slow it down, its deceleration rate. Now, where do we go from there? At that point, we have to go back to our original motion equations, our three constant accelerated motion equations, and we could use the v equals v squared equals vo squared plus 2a delta x. We know it comes to a stop, that's 0 squared. We know it's going at 20 initially, that's 20 squared. That's 2 minus 4.9 delta x. It tells us delta x is going to be, let's see, minus 400 divided by minus 9.8. That's roughly a little over 10. So it's going to be about 40, I don't know, for about 42 meters, it'll come to a stop. That's how long it takes to slide. Okay? So a sliding problem there, a little different, sort of encompasses everything. Our three constant accelerated motion equations, our friction equation, Newton's second law here, which is F equals ma, and then a free body diagram. It does a little bit of everything there. So if you can understand this problem and relating to friction, you're probably in really good shape. And just a quick note here, when they do accident reconstruction, I'm told by an officer friend of mine, they'll measure the skid marks. That's how long they know it came to a stop, how long it took, and then they can look at the weight of the car, the coefficient of friction based on your tires, and they can find friction. They can work back and find out how fast were you going when you locked them up. So just be careful out there. See you.